Okay. For 1.10.36, the easiest way to do this is to do a tree diagram. If you do a tree diagram, it all just kind of works itself out. But if you try to do it without, it's possible, but very difficult. Okay, so let's do a tree diagram. So it says we have a bunch of people that are infected with the virus. Now, of all those people that have the virus, we have 3 strains, A, B, and C. We have 0.32 or 32% with A, 59% with B, and 9% with C. So we have our probabilities for each of the strains. Now for each strain, they either have symptoms or no symptoms. Symptoms, no symptoms. Symptoms, or no symptoms. So it says 21% of the people with A have symptoms. Okay, so this would be 0.21. So if you were to write this in probability symbols, it looks something like this. So the probability that you have A equals 0.32. Now it says if you know that you have A, the probability that you have symptoms, so symptoms if you know you have A equals 0.21. So those would be the probability symbols for what we have here. Let's see. Then it says of the people that have strain B, 16% have symptoms. So if you know they have B, then 16% have symptoms. And if you know they have C, then 63% have symptoms. Okay, so you'll notice I have some branches that aren't filled in here. Well, it's easy enough to do those because each individual set of branches always has to add up to 1. So this branch and this branch have to add up to 1. So 1 minus 0.21 will give me 0.79. And 1 minus 0.16 gives me 0.84. And 1 minus 0.63 gives me 0.37. So again, each set of branches should always add up to 1. Now that we've done all of that, I like to come through and find the intersections before I do anything else. So let's see. So the probability of A and S, or A and symptoms, is going to be equal to, well, we just multiply, because it would be the conditional probability times the probability of what's given, or you just know you always multiply along the branches. So 0.32 times 0.21, which gives me 0.0672, and the probability of A and not S gives me, let's see, it's going to be 0.32 times 0.79, which gives me 0.2528. So I'm going to pause it and fill all the rest of those in. Again, just multiplying along each set of branches to find the intersections. So now that I've multiplied along the branches to find each intersection, now that I've done all that, I'm actually ready to look and see what the problem wants me to find. So for part A, it says, if a person has the virus and the person has symptoms, what is the probability that they have strain C? So we're saying we know they have symptoms. So we know they have symptoms. We're looking for the probability they have part C. Now looking at this, anytime you want a conditional probability, well, that's always going to be the probability of the and, so C and symptoms, divided by the probability of what's given. Now, sometimes, depending on if you're using Bayes' formula or not, the probability of C and S, people might write that out as C given S. Oh, sorry, that's the one we don't know yet. So we would do S given C times the probability of C. And this would all be over the probability of S. Now, it doesn't matter which way you write this out, whether you do the longer Bayes' theorem or because we've already done intersections, you just kind of skip to this, we're going to get to the same result. Because the probability of C and S, that's this thing right here, how did we find that? We did the probability of C as 0.09 times the probability of 0.63, which is the probability of S if you know they have C. So we just already did that step. So either way, we have 0.09 times 0.63 on the top. Okay. So that's the top part. Okay. Now, this is why we love the tree diagram for this next step, because we have to divide by the probability of symptoms. And the textbook did not give us probability of symptoms. That was not in our information that we had. So how are you going to find that? So to find that, we say, okay, we'll go through this tree and we will look at every probability that had an S. So if we add up these three probabilities that have S's, that should give us the probability of S, or probability symptoms. So 0.0672 plus 0.0944 plus 0.0567, those three probabilities added together should tell us the probability of having symptoms. So if we add that, we get 0.09 times 0.63 divided by 0.2183, which gives us 0.26. So if you know they have symptoms, there's a 26% chance that they have strain C, which is interesting because strain C is such a smaller part of the population, but strain C is so much more likely to have symptoms. So if you have symptoms, your chance of having strain C goes from 9% all the way up to 26%. So let's try B. It says if the person has a virus but doesn't exhibit any symptoms. So if they don't have symptoms, so that will be our given part, then what is the probability that they have strain A? So again, we're going to do the exact same thing. So conditional probabilities, this will be the probability of A and no symptoms, divided by the probability of no symptoms. So A and no symptoms. Let's just erase my marks from up above. So A and no symptoms, that would be this one. So 0.2528, which again we got by doing a multiplication. Now we need the probability of no symptoms. So we'll do it the same way as before. So we say what has no symptoms? This one, and this one. So we need to add all of those together. So 0.2528 plus 0.4956 plus 0.0333. And this should give me 0.323. And finally, part C, it says, what is the probability that someone does not exhibit any symptoms? So we're just looking for the probability of no symptoms. Our textbook called this the probability of symptoms complement. So they did symptoms complement. I did NS because I like to be able to not forget what I'm doing. So I like to use abbreviations I can remember better. Either way, this just means no symptoms. Well, they probably should have given that to us before part B, because look, in part B, we had to find that. So, oops. This 0.2528 plus 0.4956 plus 0.0333, that is the probability of no symptoms. So 0.2528 plus 0.4956 plus 0.0333 gives me 0.7817. So there you go. Again, just do a tree diagram, and then it goes back to our basic rules for conditional probability.